In this presentation, we will investigate the basics of VSDs. We will look at what they are, how they operate, when they are used, their modes of operation, and some typical issues that arise with their use. We will also go over some three-phase theory, as well as AC induction motor characteristics, as that's what VSDs typically tend to drive. Variable speed drives, also known as variable frequency drives or inverter drives, offer variable speed control to AC motors. This is done by creating an AC output of variable frequency. A motor's running speed is proportional to the frequency that you feed it. VSDs are used in many different situations. One such situation is to control processes that use electric motors. In the diagram, you can see the VSD is receiving control input from a flow controller and outputting to the pump responsible for creating the flow rate. In the renewable energy sector, power is often generated at a variable frequency. A wind turbine's output frequency varies with the wind speed. This must be converted to a specific frequency and phase in order to be fed into the power grid. VSDs also offer a simple and effective means of controlling inrush current when starting large motors. A VSD is a self-contained device that uses solid-state switching technology. In comparison to the star-delta circuit seen on the right, you can see that there is far less to install and maintain with a VSD. VSD technology became widespread in the 1980s. Before this, AC motor speed control was done using an MG, or motor generator set. This involved driving a main shaft with a DC motor. Connected to this shaft via belts were AC generators. The gear ratio of the belt connection determined the generator's rotation speed. Each generator then fed its own motor, running at its own speed. In comparison to a VSD, an MG set is expensive, limiting, and more susceptible to breakdowns. In most applications, a VSD will drive a three-phase motor. Let's revise some basic three-phase theory. A three-phase feed consists of three separate circuits. Each circuit carries a sinusoidal AC voltage oscillating at a common frequency and amplitude. The difference between each circuit is in the placement of their oscillation, or phase. Each of the three circuits is a third of a revolution, or 120 degrees, shifted from the next phase. This occurs naturally as the output of a three-phase generator. It is also consumed just as naturally by a three-phase motor, as we will see shortly. A magnetic field is created in a coil when a current gets passed through it. It follows that if you feed a coil an alternating current, the resulting magnetic field will also alternate. The frequency of the input current determines the frequency of the resultant field. By controlling the input frequency to a motor, which is essentially just an arrangement of coils, we can control its speed. At its most basic level, an AC induction motor consists of an arrangement of coils, called the stator, surrounding a magnet which is free to rotate, called the rotor. In fact, a motor has the same basic structure as a generator. The only difference is in the flow of energy. Generators convert mechanical energy into electrical energy, whereas motors convert electrical energy back into mechanical energy. In a three-phase, two-pole induction motor, you have three pairs of coils placed at 6 evenly spaced locations surrounding the rotor. Each coil pair is placed directly opposite each other. The electrical connections of each pole pair ensure that they always produce opposite magnetic polarity to each other. With even spacing, it works out that each coil pair gets positioned at 120 degree intervals around the full 360 degree rotation. The rotor gets pulled around by the constantly rotating magnetic field set up in the stator coils. Here, we can see the rotor get pulled into alignment with the coils of the blue phase when the phase current hits its peak. The force on the rotor is a result of magnetic attraction supplied by the stator coils, which in itself is a result of the current feeding these coils. The coil connections, along with the way in which they are wound, results in the pair being oppositely polarized. The frequency of the current input will dictate the speed of rotation. The formal equation for this is synchronous speed in RPM is equal to 120 times the frequency divided by the number of poles per phase. If we can control a motor's speed, we can set it up to run at the lowest speed it needs to be at to perform its task. This enables us to optimize our energy use, which has environmental and economic benefits. For centrifugal pumps and fans, the input energy is proportional to the cube of its speed. Any reduction in speed will therefore have a much larger reduction in energy use. For example, a pump running at 50% of its speed only requires 12.5% of its rated power. In a typical pumped system, the flow is controlled with a valve. The valve lowers the system efficiency by creating heat and noise. A more efficient alternative in this scenario is to control the flow directly at the pump by using a VSD and doing away with the valve. We will now look at how a VSD achieves its variable output frequency. The construction of a VSD can be divided into three main sections: the rectifier, the DC bus, and the inverter. The AC input firstly passes through the rectifier onto the DC bus, which supplies the inverter DC input. The inverter then converts the DC back into AC at the chosen frequency. This is done by applying a switching pattern on the DC bus to approximate a sinusoidal output of the desired frequency. This method is referred to as pulse width modulation, or PWM. If we were to switch a DC voltage on and off at even intervals over and over again, the average voltage would work out to be half of the input DC voltage. If we now switch the DC voltage on for only a quarter of the time and off for 3/4 of the time, our average would now be a quarter of the DC input. If we now switch it on for 3/4 and off for the remaining quarter, the average rises to 75% of the DC input. By changing the ratio of on time to off time, or pulse width, we change the average voltage output. We can vary this pulse width in such a way that when averaged, a sine wave will result. In order to smooth out the chopped up switching pattern, a filter can be placed on the VSD output. A motor's torque is its rotational power. Motor torque will decrease with increasing speed and increase with increasing voltage. Stated as an equation, we have torque equals K times voltage over frequency, where K is a constant for that particular motor. A motor's torque-speed relationship can be broken into two defined regions: the constant flux range, seen here as the flat regions of torque and flux, and the field weakening region, seen here with the torque and flux decaying away. In the constant flux range, a constant torque can be maintained by keeping the voltage-frequency ratio constant, according to the previous equation. Using a motor in this region can provide a process with VSD motor control while maintaining a constant torque. If we were to supply a constant maximum voltage inside the constant flux range, the motor core saturates, and the extra energy applied heats the motor up and decreases our efficiency. So it is a requirement that the voltage remains in proportion with the frequency inside this region. If the motor speed enters the flux weakening range, full voltage is fed to the motor and torque will drop off with increasing frequency. Using a motor in this region can be seen as a method of supplying a process with variable torque control via VSD. Even with voltage control to avoid saturation, the motor will still tend to overheat at low frequencies. Using an external fan or upgrading to a motor of larger physical dimensions can help with this by increasing the airflow over the coils. You may also consider using more efficient switching patterns, such as space vector modulation over the standard sinusoidal modulation. Without going into the specifics, certain switching patterns can improve a VSD's total harmonic distortion and efficiency, as well as being able to cope better with varying loads. A downside to space vector modulation is the introduction of a common mode voltage. At certain times, the neutral voltage of an SVM-controlled motor will not sit at neutral. The voltage will tend to leak to earth through the motor's bearings, causing damage in the process. For this reason, it may be required to fit a motor with insulated bearings and a brush commutator to provide a less harmful pathway to earth for the common mode voltage. One drawback of VSDs is that they can introduce harmonic distortion on the grid. This reduces the efficiency and quality of power delivered for every grid-connected consumer. This comes mainly in the form of 5th and 7th harmonics and is a result of the diode bridge rectifier action, along with the high-frequency switching of the DC bus. Large VSD load consumers may be required to install filtering equipment to keep their harmonic distortion within acceptable levels. Another mitigation strategy is to increase the inverter switching frequency, although the trade-off is higher switching losses. Switching patterns such as space vector modulation can also decrease switching-related harmonics. Using more sophisticated rectifier designs, such as 12 and 24 pulse rectifiers, can decrease the harmonics associated with rectification. Due to the large amplitude, high frequency output of a VSD, they are a major source of electromagnetic interference. This can disrupt nearby communication signals. For this reason, VSD cables must be properly shielded and separated from other cables. Excessive cable length can also cause voltage spikes arriving at the motor, which could potentially damage the winding insulation. VSDs offer variable speed and torque control of AC motors. They reduce power consumption, they offer favourable motor starting characteristics, and they are easy to install and maintain. They can be fed single or three-phase AC, as well as DC, making them useful for a variety of applications. The main issues with VSDs centre around heat, harmonics, and electromagnetic interference.